Okay, so today we are going to cover some theory stuff. This is going to be something that's very important in order to understand how best to select a data structure to use. All right, so the whole purpose of this course is to teach you a variety of ways to organize the information in your programs. Okay? There's not a one-stop solution when it comes to a data structure. So what you have to do is you have to look at what your program does, what it's supposed to do, its functionality. You have to look at how often you perform certain tasks. Like, for example, are you going to be entering in a lot of information frequently? Are you going to be searching for something frequently? Do you need to remove objects? How often do we need to move stuff around? Those are the kind of questions that you have to ask yourself. And based off of that, you're going to select a data structure that best fits your needs. Okay? Certain data structures are better at doing certain things. Others aren't as good at. Some data structures can't perform certain operations. And so this semester, we're going to be looking at what data structures are good for what situations. Okay? And in order for us to do that, we need a way to say, this particular data structure is good at this. Okay? But we're not going to define it in terms of good, not so good. We need a little bit more scientific way of doing that. Okay? And the way that we are going to do that is by using big O notation. Okay? And we're going to get into what that means today. And we are going to rank each data structure on its ability to perform 3 operations. Okay? We're going to say, how good are you at adding stuff to the structure? How good are you at removing stuff from the structure? And how good are you at searching for things that may or may not be in the data structure already? Okay? And we're going to come up with a notation that shows how good each data structure is at those 3 operations. The notation that we're going to use is what we're going to learn today. We're not going to get into the actual data structures. We're going to learn it, how the notation is used, and how we arrive at the values that go inside. Does that make sense? Questions? Okay, this is probably the most exciting thing that you will do all day. Or have done so far today. So, get ready for it. All right, so when we're talking about algorithm efficiency, there's really 2 different ways that we can rank or classify how efficient something is. Okay, there's time efficiency, it's also known as time complexity, and that's literally how many seconds something takes. Okay, that's how fast it runs. Start an algorithm, maybe you're sorting a million numbers. Start an algorithm, hit the stopwatch, and see how long it takes. And the other way to look at it is space complexity. It's how much memory does something take up? Okay. Now, algorithm A might be really fast, but it might take up a ton of memory. And a lot of times what you'll notice is there's a trade-off and a balance between these. Okay. You get more speed, but it takes up more memory. It takes up less memory, but it runs slower. Okay. A lot of times there's a balance between. Let me ask you guys this question. Has the need for more efficient algorithms changed over the past 50 years? Not necessarily a correct answer here, just looking for some thoughts. Go.
I remember reading Patriot Games from 1992. They talked about the laptop having 5 inch or 12 kilobits of bubble memory. So I think it's shifting more from using space efficient.
Okay, so things need to run faster. We aren't as concerned about space. Okay, other thoughts. Do we need more efficient algorithms more today than we did 50 years ago?
Yes.
You guys think so?
Yes.
Fair enough. Let me ask you this question. If you were going to write a program, and I said, I need you guys to write a very simple input-output program that asks somebody how old they are and then simply outputs what they entered. So, how old are you? I'm 90, hit enter, and it says, hi, you're 90. Real basic. How many of you would use int as the data type for the age variable? Don't lie. Come on, raise your hand. You know you would do. I would. Why would you use int?
Save space. It's quicker.
Okay. What are your options?
Double, long, short.
Short. Now, what's the maximum value you can put in an int? Anybody know?
Is it 32 to this
2 to 32.
one?
Yeah.
2 to 32. Does anybody know anyone relatively close to that old? Your dad. Yes. What's 2 to the 32? A big number.
Big number.
Let me ask you, what's 2 to the 8?
32.
1, 2, 4, 8. Anybody know anybody older than 256 that might be using this program? Yet we're going to go 2 to the 9, 2 to the 10, 11. All the way up to 2 to the 32. Bottom line is, int as a data type for age is overkill. It doesn't mean it's wrong. Technically speaking, the correct data type would be what? The most efficient, I shouldn't say correct, it's subjective. What is the most efficient, as in using the least amount of memory? Raise your hand if you've heard of short. Not like as describing how tall somebody is. What's short? So the lack of response here is indicative of the answer to question B. And what I mean by that is, we aren't taught to use short, right? How many of you were taught to use short? Nobody. The reason for that is, why?
You don't need more efficient algorithms?
Yes and no. We have memory coming out of our ears, basically. Anybody ran out of memory in a program recently?
Chrome.
One. Wow. One person. Was it on accident? Yes, it was. You're making that face. Okay. The point is, this isn't a concern for us nowadays. When we code, no one is thinking, oh, I gotta make sure I don't run out of RAM. But 50 years ago, that was a big deal. And that's why those data types exist. We have more space than we need. But time, I think we would all agree, is just as important, if not more important nowadays. So the purpose of that little story or whatever is not to say be as careless as you want with the data types that you use. In fact, now that we have, in the early 2000s, we had computers. Everyone was using computers. Spent most of the time on computers. Now we've shifted to everyone now does stuff on tablets, phones, mobile devices. Where space is a lot more important than on the computer. Not only that, but we are trying to do more and more than we used to. The more we do, the more efficient we need to be. So I would argue that we go in cycles. We have an excess of memory, we get careless, we try to do more, we need to be more efficient. Technology improves, and on that we go. Okay. Long story short, the more tools we have, the more we try to do with it. The more memory, the more computing power we have, the more we try to do with it. Okay. Yes, sir?
I was just wondering, does that have more to do with singling the mobile devices and having less space, or does that more have to do with new programs being more memory intensive than they need to be?
I think it's a little bit of both. I don't know that new programs are more memory intensive than they need to be. I don't think developers intentionally or even carelessly are inefficient. I think we try to do more and more, and we push the envelope more and more as developers, trying to be innovative, trying to do things that no one has done before, and it's kind of a learning process with perfecting how efficient things are. All right, so let's move on. The first thing that we need to do, and basically what we're going to look at today, is how we take an algorithm and analyze it. How we figure out which one's faster than something else, and the notation that goes along with that. So the first thing that we want to do, if we're analyzing an algorithm, is we want to look at the input. We want to look at the input size, and this is what's being passed into the algorithm. So if we have a basic number sorting algorithm, we're using bubble sort or selection sort or something like that, the input to that algorithm is the list of numbers that we want to sort. Okay? If we have an algorithm that takes a string and capitalizes the first letter, the input to that algorithm is the string that we pass it. Okay? So these are all just examples of what the input should be, but it's important to look at that because there's a relationship between the input and the performance of the algorithm. Typically, as the input goes up, the number of operations or the performance of the algorithm goes down. Think about if we were sorting 10 numbers versus if we were sorting 100,000 numbers. Obviously, one's going to take a lot longer than the other. All right? Look at part 3 here. Measuring runtime. So, hypothetically speaking, let's say I told you to create an algorithm. And just so that we're all clear, an algorithm is a step-by-step process for solving a problem. Whether it's tying your shoes, or baking a cake, or getting dressed in the morning, or asking a girl out on a date. Those are all step-by-step problems. Step-by-step solutions, I should say, with the goal of doing something or solving something. So if I told you to create an algorithm, and the purpose of your algorithm was to take everyone in this class and move them one seat to the left. Okay, so you would be sitting there, you would sit here, you would sit here, you would come over. Same thing. When you get to the end, you would move back there. And everyone would shift one seat over to the left. Okay? Obviously, there would be some stipulations, like you can't move somebody on top of somebody else. So before you could move here, the seat has to first be empty. You would have to move first, and so on. So if I gave you 10 minutes to do that, after that time, we wanted to see who could come up with the best algorithm for doing it. How would we determine that? How would we figure out who did the best? So what if we, first thing we look at is, let's just look at time. So, I think I need to. Both of you have an algorithm that you've written. They're different, but they both solve the problem. When you're done, everyone has moved one seat over to the left, and it works. So we'll start with you first. I take your algorithm, and I read out the instructions, and as I read out the instructions, you guys do what you need to do. So I'll say, okay, you move, and you move, you move. And we start the stopwatch. I walk through the whole thing, and it's fine. We finish, and let's say it takes 2 minutes and 32 seconds. Okay, so your algorithm took 2 minutes and 32 seconds. Now we want to do yours. We start off, I'm reading the instructions, people are moving seats, everything is going well. It seems to be running faster than yours, faster than the first one. Okay? But when we ask Jameis to move seats, he trips, falls, breaks his leg.
That never happens.
It takes him so long to move to the seat that we almost lose track of time. So it takes him like 5 minutes to get from one seat to the other. His leg is breaking. He's crying a little bit. He finally gets into the seat, and the rest of the program finishes. Total time, 7 minutes and 12 seconds. Thanks. Whose algorithm was better? I don't know. Well, when you look at time, clearly the first one was. But we also had a hiccup in our program. And you say, well, that wouldn't happen in a real program. No one's reading off instructions. There's not that human screw up. No one's going to make a mistake and trip over something. You can't accidentally, misplace something when you're coding. The environment doesn't play an effect on how fast an algorithm runs, right? Anybody ever go to do something, maybe start up a program, maybe get ready to watch a video or something, and Norton decides that it's a good time to run a virus scan? Okay. Or, now's a good time to install updates. Windows is going to shut down. Well, what if that happened to us? What if we said, okay, we know that there's a human element to it, so let's code those two algorithms, and let's run them, and let's just see how long they take. You run the first one, okay, takes this long. Run the second one. As it's running, your computer decides to do a bunch of stuff. Okay? Maybe that's the time that Windows decides to download the automatic updates. It's going to mess it up. Because while your computer is running, all of this other stuff is running too. So yeah, there's not a human element, but the environment certainly plays an impact on how fast something runs. The other programs that we've got running. We all know Chrome is awesome for taking up resources. The point I'm trying to make is time as a basis for determining which algorithm is better is problematic at best. And people figure that out really fast. Not to mention your computer might be way faster than mine, so if we both run the same thing, it's going to run faster on yours than it is mine. Or maybe your computer architecture is different than mine. Might not necessarily be faster, but the bottlenecks in my system prevent it from running as fast, or certain things go faster on mine than they do on yours, or vice versa. Long story short, what they came up with was, instead of using time as a basis for comparing two algorithms, a better thing to do is look at the steps. So how many steps are we doing? So as they look at the steps, what they realized was a lot of steps in an algorithm aren't really important. Maybe you only run them once, or maybe they don't run as often as others. And so this led to the idea of what is known as a basic operation. This is important. You need to know what this term is. The basic operation of an algorithm is the operation, line of code, action, command, whatever you want to call it, that contributes most to the total runtime of the algorithm. It is what is done over and over again. So, has everyone done at least one sorting algorithm? Sure. Basic operation is the operation that contributes most to the total runtime of an algorithm. One operation. I'm not saying there's only one operation in an algorithm. You guys know there can be tons. You're going to isolate one and say that's the one that contributes most. So if we're looking at a sorting algorithm, everyone done at least one sorting algorithm? No? Yes? Sorting algorithm? Okay. What are you doing over and over in a sorting algorithm? Compare it. That's right. Are you bigger than you? Are you bigger than you? And you just, whether you're swapping or there's dozens of sorting algorithms, whatever it is that you're actually, however you're managing or switching the numbers, you're comparing over and over again. So that if statement that compares the two numbers, that's your basic operation. Right? And we're going to look more next class about how we identify what a basic operation is. But I just wanted to cover the term now. Okay. Any questions on this? We good? All right, let's move on. So the next topic we're going to look at is we're getting ready to get into the notation. we're going to take a look at what is known as orders of growth. When we examine and compare and rank and analyze algorithms, we are not interested in how long it takes or how many operations it's going to run when the input size is small. Okay. If you're sorting 10 numbers, it doesn't matter what sorting algorithm you're using. But as that input size increases, as you go from sorting 10 to 100 to 10,000 to 1,000,000, the performance of the algorithm grows. And the number of operations that it runs as the input size increases changes. Okay, you guys remember doing limits in calculus? A lot of scared faces. Bad memories. What you were doing is you were graphing how those functions changed as the input variable approached what? Infinity. So as it grew, the function grew. And the curve is what we're looking at. We want to know how many operations it's going to run, how that curve changes as we increase the input size. So here's an example. Hypothetical situation. You have two people that are washing dishes. Each of the two individuals gets the job done. When they're finished, the dishes are clean and dry. But they go about it different ways. They have two different algorithms for how they wash dishes. First person works like this. Okay. They pick up a dish. It takes them 30 seconds to wash it. It takes them 30 seconds to dry it. And then they put it down and they're done. Second dish, 30 seconds to wash, 30 seconds to dry, they put it down and they're done. Third dish, 30 seconds done. Takes them 30 seconds to wash a dish, 30 seconds to dry a dish, and they're finished. Okay? The second person is careless, as it says. Now it still takes them 30 seconds to wash and 30 seconds to dry a dish. Okay, so the speed of performing the actual operation is the same. But here's the difference. When the second person washes a dish, 30 seconds, they splash water all over the place, including the area where they put the dry dishes. So it works like this. Pick up the first dish, wash, 30 seconds, dry, 30 seconds, put it down. Done. Pick up the second dish, wash, 30 seconds, dry, 30 seconds. Now you also have to pick up the first dish and dry it again, 30 seconds, and put it down. Pick up the third dish, wash, 30 seconds, dry, 30 seconds. Pick up the second dish, dry it. Pick up the first dish, dry it, put it down. Now you would think they would figure it out after the first couple of dishes, but they don't. Pick up the fourth dish, wash it, dry it. Third dish, dry it. Second dish, dry it. First dish, dry it. Done. Fifth dish, and so on. So I think you can see, as the input increases, the second person's work grows much faster than the first person's work. Let's take a look at the math of this. So, first question, what's the input? What is the input to this?
Dishes, number of dishes.
Number of dishes, very good. The number of dishes is the input to this algorithm. How are we going to measure running time? It gives it to us in the problem. Seconds, right. So we're going to measure it in seconds. So let's take a look at the first person. The time it takes for them to wash n dishes is equal to n, which is the number of dishes we're washing, times 30 seconds to wash, 30 seconds to dry. This simplifies to 60n seconds. We can rewrite this as f of n equals 60n, where f, the function that we are modeling here, is washing dishes. I promise, well, there is some mathy stuff like this in the course, but it's not a ton like this. Most of the course, but we have to do some of this stuff. So we are going to model the first person's algorithm as f of n equals 60n. Questions on this? This is important. Circle this. If you're taking it, circle this and write functional notation. Functional notation. This is person one's algorithm expressed in functional notation. I'm going to reference functional notation frequently in the next couple of days, next couple of class periods. And the reason for that is part of the process for analyzing an algorithm is getting it first in functional notation and then doing stuff with it. Okay? So this is functional notation. Typically speaking, you can use whatever letter or word you want here. A lot of times they use F for function, but you can put Q, you can put dishwashing, whatever. It doesn't matter. A lot of times in computer science, you'll see N here as some arbitrary number. In math, it's typically X. It doesn't matter. Put whatever thing you want here. Put dishes if you want. It helps you remember. Questions on this? We good so far? All right, let's look at the second person. We know the second person's algorithm. We know how it works. So the time it takes them to wash n dishes is 30n plus, so 30 seconds to wash, plus 30n to dry, multiplied by the number of dishes divided by 2. The math isn't important. Okay? That's not the purpose of this course. I'm not going to give you this and say, come up with the math that illustrates their algorithm. Okay? Long story short, their algorithm comes out to this. Okay, so I'm not concerned with how we get here. That's for your math classes. I want to focus on what we do with that. So we have f of n equals 15n squared plus 45n. That's what it simplifies to. So now that we have both algorithms expressed in functional notation, let's move on to the next step. And what we want to do, and I mentioned this a little bit ago, we want to focus on the general nature, how the function grows as the input increases. Okay? So if we look at this, our input is n. So we want to see how increasing n affects the algorithm. Here's how we do that. So we're going to look at the portion of the function that changes the most, as n increases. Right, let me just that a bit. So look at our two functions. Once you have your algorithms in functional notation, the next thing you want to do is pick out the dominant term. Okay, you have to write that down here. Once you've got them in functional notation here and here, the next step is identify or pick out the dominant term. The dominant term, like the basic operation, is the term that contributes most to the growth of the algorithm. Okay? And there are some rules and guidelines for how you pick out the dominant term. The first thing you do, if you look at this, the first thing you do is you ignore any constants. So if we're looking at this first one here, we have 60n. 60 is a constant, so we ignore it. The reason we don't care about constants is because we're interested in how the algorithm grows. As n increases, how does it affect it? Constants, by definition, don't change. So as n increases, the constant stays as is. So it doesn't have an impact on the growth. We're not interested in it, so we ignore it. The only thing we're left with is n. That's our dominant term. That was an easy one. Let's look at the second one. We have f of n equals 15n squared plus 45n. ignoring the constants leaves us with n squared plus n. Which of the two is larger? N squared. Our dominant term in this case is n squared. Easy stuff, right? Any questions on that? Okay. That kind of summarizes what we just said. And we want to pick up the term that contributes most. Now, let me reiterate this. The purpose in us doing this is to focus on how the algorithm grows when the input is really large. When we say that n squared is the dominant term for the second person's algorithm, that just means that it contributes most to its growth as the input increases. If n is 2 or 1, it's not going to be the largest contributor. Okay, because we have 45n, 15n squared. If n is really small, the 45 is going to tip it in favor of the other one. But we're not interested in small input sizes. If we're washing 2 dishes, who cares what algorithm we use? It's very negligible. We're interested in large numbers. Okay, does that make sense? Now, after you picked out the dominant term, the final step is to express the algorithm's complexity using what we call big O notation. Okay? Now, really simple. Here's how you do it. Big O notation is a capital O, or a big O, as opposed to a little o, which is followed by a set of parentheses. Inside the parentheses, you put the dominant term that you picked out in the previous step. So the first person's algorithm is ON. Second person's algorithm would be what? ON squared. Very good. So you guys remember back to the beginning of class when I said the purpose of this course is to teach you a variety of data structures and give you the tools that are going to help you pick out what data structure is best for your particular program. We are going to evaluate each data structure on its ability to add, remove, and search for things. Every algorithm in the world, including adding, removing, and searching for all of the data structures that we're going to cover, has a complexity for each of those operations. We look at the complexity and we compare that against the complexity of the same operation for the other data structures in order to figure out which one makes the most sense for us. Conceptually, does that make sense? Okay, we haven't talked about specifics. We haven't talked about all the different notations there are. But overview, that's the purpose of this course, and that's why we're learning this right now. Okay. I can't prove to you that one data structure is better than another in a given situation if I can't say the cost to add in this data structure is ON and the cost to add in this data structure is ON squared, so clearly this one is better. Okay. This is basically our proof for an algorithm being better than another one. Okay? You'll see this a lot. All right, give me 1 second. Let me figure out. All right, I want to look at this real quick, and then we'll come back up to that top stuff. This chart shows you the 8 different orders of growth or classes that an algorithm can belong to. Every algorithm in the world will fit into one of these 8 categories. So we looked at two so far. We looked at ON and ON squared. So person one's algorithm is ON. You could say it's a linear function, linear growth. Person two's algorithm was down here at n squared, quadratic growth. And you guys took calculus, you've seen this stuff before. You might have a vague recollection of what a log function looks like graph. Okay. That's its growth. That's how the algorithm grows. We're going to be looking at it from a computer science standpoint, or you guys looked at it from a math standpoint. Again, every algorithm in the world will fit into one of these categories. Okay. Let's do this. This is really important. And this is something that we are going to review several times. Okay? I won't tell you to write down a lot of things and understand a lot of things, but this is one of them. Knowing that, if I say we have two algorithms, one's ON and one's ON squared, it's easy to see which one is better. Okay? Clearly, n squared is better. Okay, you're good. I'm sorry, clearly n is better than n squared. But what I want you guys to understand, or I want you to get a little bit more out of just looking at two algorithms and knowing that n cubed is worse than n squared, and log n is better than n, and that sort of thing. Right? That list I showed you a second ago, they're listed in order of how fast they run. Basic algebra, you guys should know that. If you don't know that, know the list. Okay. But what does big O really tell us about the algorithm? Practically speaking. And so what I want to do is just break this down a little bit. Let's say we have an algorithm that's ON, like our first dishwashing algorithm. Big O notation shows the relationship between two things. In terms of actually coding this, actually looking at how the algorithm runs and its effect on the number of operations, knowing the big O notation, this is also referred as the complexity, knowing the complexity or the order of growth of an algorithm tells us two things, or shows us the relationship between two things. The first is the input size. Shows the relationship between the input size. And the second is the number of basic operations, or the number of times the basic operation is run. So let me see if I can clarify this a little bit. When we are given, or we determine, the complexity of an algorithm, we say, okay, it's ON, and we'll look at how we do that next class, right, specifically. Something is ON. That tells us the relationship between the input size and the number of times the basic operation runs. It tells us the growth. The relationship is shown by the term. So as I increase the input, the number of basic operations increases by this amount. So a linear, or ON, is a one-to-one increase. If I have 10 numbers, and it takes me 10 operations, and then I increase the input to 100, how many operations am I going to have? 100. Okay? If it's ON, that means as I increase the input, we have a likewise, or a linear increase in the basic operations. And this is important because we need to know how changing the input size is going to affect performance. If your boss comes to you and says, okay, our client base currently has 10,000 emails, and we send out 10,000 emails, or we send out emails to 10,000 different clients, right? And we are looking at going to a trade show and we expect to add another 30,000. Can our current algorithm for sending out emails handle that? I don't know. Look at the algorithm that you're using for sending out emails. The input is 10,000, and you know how many basic operations it is. You know the complexity of the algorithm. Then you know how increasing the input by 30,000 is going to affect the number of basic operations that it runs. And that'll tell you whether or not you need to change things. On the other hand, if we've got ON squared, 10 operations, input size of 10, the number of operations is 100. What happens if I go input size 100? How's that going to affect this? 100 squared. Because the relationship between the input and the number of basic operations is the term of the complexity. Does this make sense? Are there questions on this? We're going to do a lot more with this, but I wanted to at least put it out there now. Okay. What I want you to take away from this is that when you're looking at the big O notation of an algorithm, if you're looking at the complexity, you know that that complexity shows you the relationship between the input to the algorithm and the number of basic operations that's going to run. Last thing I'll say on this before we move on. The fastest, most efficient algorithms are O1. And if you look at the list back in the topic outline, this is the one that was on the top. It's known as constant time. It's the only one that doesn't have an N in there. And the reason for that is this doesn't mean there's only one operation. Okay, that's a common point of confusion. It doesn't mean that the algorithm only runs one operation. The one just represents constant time. It could run 3 operations at a time. The point of this is constant time means the number of times the basic operation runs is not affected by the input size. So whether you are doing something with an input size of 10 or 100 or 1,000,000, you always run the same number of basic operations. All right, let's go back. Told you this was exciting stuff. We're getting close to being done. See, the people watching the video, they can just pause it and take a nap. You guys don't have that luxury. Unless you watch it later. All right, so as this pulls up, we have one more thing left to talk about, and then we're going to do a couple practice problems, just one, and then we will look at your homework. So I want to cover the idea of best case and worst case, and touch briefly on average case. Some algorithms, not all, some algorithms are going to run different numbers of operations even though the input size is the same. So first of all, think about sorting a list of 10 numbers. You just want to sort. We already talked about the basic operation being the comparison between two numbers. Are you less than you, are you less than you? In sorting algorithms, the number of comparisons we perform will always be the same. So if we've got 10 numbers, we will always run the same number of comparisons with that algorithm. This is different from a lot of searching algorithms. Here's what I mean. Let's just say this class were broken down into an array, where each student is in a different element of an array. And I wanted to find the first student that had a birthday in March. I would typically run something simple like a sequential or a linear search algorithm. It's a fancy way of saying start at the beginning and look at each one until you find it. So we're going to start at the front. Is your birthday in March? I say March. Yeah. Your birthday in March? Nope. March? Nope. March? Nope. Nope. March? Nope. Nope. March? Nope. March?
Yeah.
Yes. Found one. So we went 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 operations before I found one. Now, typically in linear and sequential search, when you find one, you stop. Okay? Now, again, this is different from from sorting. In sorting, even if the list is already sorted when we pass it in, we still have to go through the whole algorithm. Okay? And the reason for that is the cost to check to see if it's sorted is just as expensive as actually sorting it. How many students are in this class? Roughly 60. I don't know. Worst case scenario, how many operations would I have to run before I found someone with a birth date in March? Worst case scenario. 60. Worst case scenario is no one in here has a birthday in March. So I have to check all 60 and everybody says no. Best case scenario, his birthday's in March. Right? Is it? Or when is your birthday? May. So you know. Point being, certain algorithms, not all, will have a distinction between the best case and the worst case. A lot of algorithms, like sorting algorithms, there is no distinction between the best case and the worst case scenario. Some are, some aren't. Conceptually, again, does this make sense? The idea of best case and worst case. Now, we could touch briefly on the idea of average case, but it's a little bit more complex than you might think. So, in the example that we just had, if we wanted to go through each month of the year and find the first student that had a birth date with that, or a birth month that matched the one that we were looking for, we know best case scenario would be 01, one operation. Worst case scenario would be ON. I have to check everybody. What would the average case? So if there's 60 students in here, best case is one operation, worst case is 60 operations. What do we expect the average case to be?
60 divided by 12?
Let me rephrase the question. Let's just look at a single month. Okay? Instead of looking at all 12 months, let's just look at a single month. And then let's look at every classroom that's in session right now at UNC Charlotte. And we want to know how many operations, what is the average time it takes to find someone with a birth date in March. Okay, so let's just assume there's another class meeting over here. We had to do 8 operations before we found one here. They might have to do 32 operations before they find someone with a birth date in March. Someone else might have to do 1 operation. Another class might have to do 54. What do we expect the average is going to break down to? Think about it a second. How many of you have taken stats, 21, 22? A little less than that. You would expect that it's going to resolve somewhere around n divided by 2. It's going to resolve somewhere around the middle. You know, half the time it's going to be early on, half the time it's going to be front and back. In order to truly answer this question, you have to know the probability that someone with a birth month on the one you're searching for actually exists in there. Okay. It goes a little bit beyond the scope of this class, but be aware that average case is a thing. We're not going to do much with it. In fact, this might be the last time we talk about it. Okay. What I want you to take away from this is knowing that there are certain algorithms that have a distinction between the best case and the worst case. Some algorithms are going to stop early, but have the chance to actually have to go all the way through. Okay? In some algorithms, there is no distinction between the best case and the worst case scenario. Any questions on this? All right, let's do a practice problem. You can read a little bit more about best case, worst case outcomes. All right, practice problem. There are 22 gloves in a drawer. So we've got a glove drawer. 5 pairs of red gloves, so 10 red gloves. 4 pairs of yellow gloves, 2 pairs of green. Good so far? You select the gloves in the dark. It's best just not to ask why in a lot of these questions, but why you have a drawer full of gloves and why you're picking them out in the dark. Maybe you spent all of your money on gloves and didn't pay your electric bill. Either way, you select gloves in the dark and can check them only after a selection has been made. Okay, so you pick out the glove one at a time, and you can look at them only after you pick them out. What is the smallest, i.e., best case scenario? The gloves match. And what is the worst case? Okay, so what is the smallest or the fewest number of gloves that you have to pull out, best case scenario, in order to get gloves that match? And what is the worst case, as in the maximum number of gloves you have to pull out before you get a match? Okay? Think a second. Just let everyone take just a minute. So again, you got a bunch of gloves in the drawer. You pick one out. You pick another one out. What is the fewest number of gloves you have to pick out, best case scenario, to get a match? And what is the most worst case scenario you have to pull out in order to get a match? Okay. So best case is easy. Right? How many do you have to pull out before you get a match? 2. Well, you pull out one and you pull out one. Okay. Now, think about this one. The worst case scenario. So think a second before you answer immediately. Worst case scenario, what is the maximum number of gloves you can pull out before you get a match? 12. 12? 4?
10.
10?
10.
10?
4.
4? 10. Raise your hand if you think it's 4. Raise your hand if you think it's 10.
11.
11. 12?
5.
8. Throwing out numbers. There's 2 answers to this, depending on how you think about it. Okay, so we'll take 2 different answers.
Or 22.
Yeah.
Or 22. Yeah. The worst, or look at it this way. You can get 2 different answers depending on how you visualize the gloves. Okay? Depending on whether or not you view these gloves as being able to be put on either hand. Okay, so are they mittens or are they like ski gloves? So if you can put them on either hand, okay. If you can put them on either hand, then what's the answer? 4. Pull out the first one, it's red. Pull out the second one, it's yellow. Pull out the third, it's green. The next glove you pull out has to be either red, yellow, or green.
Say that one more time, please.
Okay? You pull out the first glove, and let's just say it's red. Now, you know if you pull out another red glove, you've got a match, so that's no good. So you pull out a green glove. Okay? If you pull out a red or a green, you know you've got a match, so you pull out a yellow. You've got 3 different gloves. You know the only thing left in the drawer, red, green, and yellow. So the next glove you have to pull out has to be red, green, or yellow, and it's going to match one of the gloves that you have. That's if you can put gloves on either hand. Okay, so the fourth glove you pull out is green. Put your first green glove on this hand, second green glove on this hand, and you've got that. Now, if you look at gloves as only being able to be put on a single hand, as in there is a distinction between left gloves and right gloves, then you get a different answer. You pull out all 5 red left gloves. And then you pull out all 4 left-handed green gloves. And then you pull out both of the left-handed yellow gloves. That's 11. The 12th glove that you pull out has to match the yellow. Okay? So there's your answer. Either would be fine, depending on how you justify it. Okay. Questions on that?
So which one was the worst? Like what number? What's 4 or 11?
4 or 12. The way I worded it, I mean, 11 is the number of gloves that you pull out before you pull out a match. So technically, the 12th glove makes the match. You got a question?
Because the way it sounded, I thought you were like, you pick up one, then pick out another, turn on the light. If it didn't match, put it back, and restart again.
That's it.
Yeah,
That's what I thought it was saying.
that would be the equivalent of like BOGO sorts. Have you guys heard of BOGO sorts? BOGO sort is it's a sorting algorithm. It works like this. You take an array. The goal is to have it sorted. And you randomize the placement of the numbers. Just mix them up. And then you check to see if it's sorted. If not, you start over. Re-randomize it. Is it sorted? No. Re-randomize it. Is it sorted? No. You just keep doing that until it's sorted. It's not a real algorithm. Well, I guess it is, but that would basically be the equivalent. It could go on forever. Worst case scenario would be you never pick out a match.
Yeah, that's what I was thinking. I thought that was the answer.
I got you. My fault. I didn't explain it very well.
I'm sorry, can you go over the worst case? Because I'm getting confused when it's like 4 mittens or just 11 or how many second gloves that you could get.
Are you want me to go over the left-handed, right-handed?
I guess, yeah.
Okay, so worst case scenario, the maximum number of gloves that you have to pull out. So let's just say the first 5 gloves you pull out a left-handed right glove, another left-handed right glove. They're both red gloves, but they don't match because you're both left-handed. Another left-handed, another left-handed, another left-handed. So you got 5 left-handed red gloves. Okay? And then you do the same thing for the yellow. So you pick out one, it's a left-handed yellow. You pick out another, it's a left-handed yellow. So you pull out 4 left-handed yellow gloves. Okay? Really bad luck here, but that's worst case scenario. Okay? So now you've got 5 left-handed red gloves, 4 left-handed yellow gloves. No matches so far. The next 2 gloves that you pick out are left-handed green gloves. So you've got 11 gloves that don't match. The only thing left in your drawer at this point, because you know that there's a total of 22 gloves, are right-handed gloves. You've got 5 right-handed red, 4 right-handed yellow, 2 right-handed green. No matter what glove you pick out at that point, it's going to match one of the 11 left-handed gloves that you've picked out so far. Does that make sense? Yeah. So the 12th glove, or worst case scenario, you have to pull out 12 gloves before you have a match.
I was thinking that the first one you have to get a red pair of gloves. I thought that's what it was.
No. Okay. Well, if that were the case, worst case scenario would be 22. You have to pull out all of them.
Yeah.
All right. Let's take a look at your homework. So you have 2 questions for homework. So if you look on Canvas and go to assignments, And homework number 1, algorithm analysis. These 2 questions are right here. They're the same 2 things that are right here. I just put them in this so that we could go over it in class. How you submit this is up to you. You can write it by hand, scan it, take a picture of it, upload the picture. You can type it in. Can be challenging because you have to do some symbols. Let's go over the first one. Imagine after washing 5 distinct, different pairs of socks, you discover that 2 socks are missing. Okay, so maybe you have a red pair of socks, a green pair of socks, a blue pair of socks, whatever. Distinct socks. It's not like you have 10 black socks and they're all can go together. 5 distinct pairs of socks. Of course, you'd like to have the largest number of complete pairs remaining. Thus, you're left with 4 complete pairs in the best case scenario and 3 complete pairs in the worst case scenario. Okay, so, best case scenario is the 2 socks that you lost matched. And you're left with 4 complete pairs. Worst case scenario, the 2 socks that you lost didn't match. So you have 3 complete pairs and then 2 socks that don't match. Does that make sense? Yes? No? Okay. So, you're going to answer 2 things. The first is, what is the probability that the best case scenario occurs? Second thing is, what is the probability of the worst case scenario occurring? Logic would tell you that these probabilities have to add up to 1. So one of the 2 has to happen. Either it's best case or worst case scenario. Okay? So if your best case scenario is 30%, your worst case scenario is 70%. Right? Here's how you go about solving this. Some of you have taken or are in statistics, but what you need to look up are combination problems, permutation and combination problems. There's a formula for this. You have to use that. Some of you probably remember it. Let me offer you a little bit of advice. Don't try to figure this out in your head. You're going to get it wrong. There are formulas for a reason. Every semester, there are students who are like, I don't need that formula. I don't even mess with looking at it. I hated statistics. It confused me. I'm just going to figure this out and get it wrong. You're going to get it wrong. Google permutation and combination. I'm going to challenge you, but I'm going to get it right.
I did get it right, and I didn't.
You are an exception to every rule. So it doesn't even do any good to say, unless you're really smart, your TA is an exception. Be careful, but look up permutation and combination problems. Yes, sir.
So, like for the formula, we were to use the calculator, would that not, like?
That's fine. So here's what I want to see in terms of work. Okay. Show me the formula. Okay. It involves factorials. Okay. Factorial over factorial. Well, it's just plugging this up. That's fine. Just show your work. All right. All that we want to do is see how you arrived at the probability. Okay. You can express the probability as a percentage. You can express it as a fraction. That's fine. We just want to see how you got what you got. Does that make sense? You have to show some sort of work. So,
We're trying to get it on Moodle, right? Or
Yes.
in-
on Canvas. Just upload it to Canvas. You can either type it in, you can work it out on paper, take a picture with your phone, upload it that way. Completely up to you. Okay? Questions on the first problem? You've got 2. All right, second problem. According to a well-known legend, the game of chess was invented many centuries ago in northwestern India by a certain sage. When he took his invention to his king, the king liked the game so much that he offered the inventor any reward he wanted. The inventor asked for some grain to be obtained as follows. Just a single grain of wheat was to be placed on the first square of the chessboard, 2 on the second, 4 on the third, or 8 on the fourth, and so on, until all 64 squares had been filled. If it took just 1 second to count each grain, how long would it take to give all of the grain due to him? This is your homework. Okay, yes?
Can we do the Gauss school child shortcut?
You need to show your work. And I think the math would get out of hand real quick if you did it that way. You can try it. He's talking about take the last and first, subtract and come to the middle. You need, everyone taking Calc 2? Okay, if you haven't, all of you have done summations before, right?
Yes.
Okay? This is a summation problem. Look at how it's growing. 1, 2, 4, 8, 16, 32, 64. This is a binary. Look at how it's growing. Okay? It's a summation problem. What we want to see in terms of work for this, simply show us the summation. That's fine. Questions on this? Again, this is due night before your next class. I think it's Monday. Monday at 11:55. Turn it in on Canvas. Homework is not taken late. The lowest one gets dropped, but we don't take late homework because we go over the next one. Okay? Questions for me? All right, have a good weekend. I will see you guys.